Hi everyone. In this video, we'll solve the find peak element problem in O log n, using a clean binary search. We'll walk through the code line by line and then simulate it on an example. Let's go. We're given a 0 indexed array nums. A peak is any element strictly greater than its neighbors. Edges are treated as outside the array, so the first and last elements can be peaks. We need to return the index of any peak, and do it in O log n time. Also, numSci is not equal to numSci plus 1, so no equal adjacent values. Big idea. Binary search works because when you compare numsmid and numsmid plus 1, you can tell which side must contain a peak. If numsmid greater than numsmid plus 1, you're on a descending slope. A peak exists on the left, possibly at mid. If numsmid less than numsmid plus 1, you're on an ascending slope. A peak exists on the right. Line by line. Type inting, optional but helpful. Function takes the array and returns the index of a peak. Standard binary search boundaries. We loop until our search window collapses to a single index. Middle index. Integer division keeps it in range. Compare the middle element with its right neighbor. This is safe because the loop condition guarantees mid less than right. So mid plus 1 is valid. If the slope goes down to the right, a peak is on the left half, including mid. If the slope goes up to the right, a peak is on the right half, excluding mid. When left equals right, we've pinned the search to a single index. This is a peak. Walkthrough example. Let's walk through the algorithm with an example step by step so you can clearly see how the binary search narrows down to a peak. Example 1, nums equals 1, 2, 1, 3, 5, 6, 4. Our goal is to find the index of a peak element. In this array, the valid answers are index 1, where the value is 2, or index 5, where the value is 6. Both are peaks. We start by setting our 2 pointers. The left pointer is at 0, the beginning of the array. The right pointer is at 6, the last index of the array. Now we enter the loop. First step. We calculate the middle index. 0 plus 6, divided by 2 gives us 3. That means mid points to the element at index 3, which is the value 3. Next, we compare this element with its right neighbor at index 4. So we compare nums3 equals 3 and nums4 equals 5. Since 3 is less than 5, this means we are on an ascending slope. Peaks lie in the direction of the slope going up, so we move the left pointer to mid plus 1, which is 4. Second step. Now our search range is from index 4 to index 6. We calculate the new middle index. 4 plus 6, divided by 2 gives us 5. So mid is at index 5, which has the value 6. Compare this with the element to the right, num6 equals 4. Since 6 is greater than 4, this means we are on a descending slope. A peak must be to the left side, possibly at mid itself. So we move the right pointer to mid, which is 5. Third step. Now our search range is from index 4 to index 5. Calculate the middle index again. 4 plus 5, divided by 2 gives us 4. So mid is at index 4, which has the value 5. Compare it with its neighbor at index 5, which is 6. Since 5 is less than 6, we are on an ascending slope again. That means the peak is on the right, so we move the left pointer to mid plus 1, which is 5. At this point, the left pointer and the right pointer both point to index 5. That is our peak. We return 5, which corresponds to the value 6. Example 2, nums equals 1, 2, 3, 1. Let's try a quicker second example. Start with left at 0 and right at 3. Calculate the middle. 0 plus 3, divided by 2 is 1. Compare nums1 equals 2 with nums2 equals 3. Since 2 is less than 3, we are on an ascending slope, so we move left to 2. Now left is 2 and right is 3. Calculate the middle again. 2 plus 3, divided by 2 is 2. Compare nums2 equals 3 with nums3 equals 1. Since 3 is greater than 1, we are on a descending slope. That means the peak is on the left side, so we set right equal to mid, which is 2. Now left and right both equal 2. The algorithm stops and returns index 2, which corresponds to the value 3. Edge cases. Let's quickly talk about some edge cases that the algorithm handles naturally. Single element array. For example, 7. In this case, left and right both start at 0. The loop never runs, and the function immediately returns 0. That makes sense, because the only element is by definition a peak. 2 elements. 4, 1, 2, the algorithm compares the first element with the second. Since 1 is less than 2, it moves left to the right side, and returns index 1. 4, 2, 1, the algorithm sees that 2 is greater than 1, so it moves right to index 0, and returns 0. Both are correct peaks. Strictly increasing array. 4, 1, 2, 3, 4, the slope is always ascending, so the algorithm keeps moving the left pointer forward until it reaches the last index. The last element is returned as the peak. Strictly decreasing array. 4, 4, 3, 2, 1, the slope is always descending, so the algorithm keeps moving the right pointer leftward until it reaches the first index. The first element is returned as the peak. Why is it safe to check nums mid plus 1? This is an important detail. Our loop only runs while the left pointer is less than the right pointer. That means the middle index is always strictly less than the right index. Therefore, mid plus 1 will never go out of range. We are guaranteed that nums mid plus 1 is a valid element. Slope argument. Each comparison tells us which half must contain a peak. We never discard the side that could contain it. This invariant guarantees we converge to a peak. Complexity time, O log n, each step has the search space. Space, O1 we use just a few pointers, no extra data structures. That's the peak element problem in O log n, with a neat binary search. If you found this breakdown helpful, hit like and subscribe, and drop a comment with the next algorithm you want explained.